Hello and welcome to the channel. Every IT enthusiast needs a Homelab server to learn and practice skills like Linux administrations, networking, containerization, and more. You can try out tools like Docker, Kubernetes, Ansible, or Terraform without risking production environments. A Homelab server also lets you solve real-life needs while learning. You can host your personal website or blog, stream music, photos, or videos, or even run dedicated game servers for multiplayer gaming. Platforms like Home Assistant can help you control IoT devices and set up automations. You can also build a NAS for centralized file storage or backups, create your own private cloud, or set up a VPN for secure access to your home network. On top of that, you can use tools like Grafana and Prometheus for monitoring, learn to configure firewalls, routers, DNS filtering, and even dive into cybersecurity. Beyond the practical benefits, it's a rewarding hobby. Combining technology with your personal interest is both fun and fulfilling. In this video, we'll be building a lightweight Kubernetes cluster on a single node using K3s. We'll also expose our services to the internet with a CloudflareD tunnel and use the Traefik Ingress Controller for internal traffic routing. This will act as a base for deploying and managing various containerized applications. My name is Philip. Let's get started. Let's start by discussing why K3s is a great choice for a Homelab server. You could use a virtualization platform like Proxmox to install virtual machines. Proxmox was very popular about 10 years ago. While it's a fantastic product and still has its place, it's heavy on resources and not ideal for automation. It wouldn't be my first choice for Homelab server in 2025. A better approach is running containers with Docker and Docker Compose. These are lightweight and excellent for managing containers, but they lack the advanced features needed to build efficient clusters or handle more complex workloads. If I were building a Homelab today, I would go with Kubernetes, specifically K3s. Kubernetes has become the industry standard, making it essential to learn. It's highly scalable, supports easy automation, and is perfect for running containerized applications efficiently. K3s, being a lightweight version of Kubernetes, is ideal for home labs and smaller setups. There are a few things you'll need to get started. First, you'll need a domain. I highly recommend purchasing one as it's cheap and essential for many tasks you'll be working on. Next, you'll need to update your domain's DNS server to Cloudflare. I've linked a video that walks you through this process in detail. You'll also need to sign up with Cloudflare Zero Trust. Finally, you'll need a machine running Linux to host your K3s cluster. You have several options here. It could be an old PC or laptop, a small form factor PC, or a virtual machine if you already have VMware or Proxmox set up. You could also use a cloud VM. Oracle Cloud, for example, offers an excellent free tier. You can use a mini PC like Intel NUC or thin client such as this HP T730. However, for this video, we'll be using the NanoPi T6 single board computer. It's all about performance to power consumption ratio, and you simply cannot beat ARM CPU in that regard. These SBCs have incredibly low power consumption. Keep in mind that most SBCs these days use ARM64 architecture, so the containers you run need to be built for ARM. If a maximum compatibility is a priority, you might want to choose a thin client or something like an Intel NUC, which is an x86 based. The minimum requirements to run K3s are 2 cores and 2 gigs of RAM. For our setup, we'll be using 8-core CPU, 8 gigs of RAM, and 250 gig of NVMe storage. Of course, the exact specification will depend on the workloads you are planning to run. One thing you don't need is a static public IP, as Cloudflare tunnel will handle that for you. Alright, let's get started. Let's walk through the K3s installation process. Kubernetes relies on precise memory management, so to ensure stability and predictability in resource management, we'll start by disabling swap on the node. First, I will open the etcfs file. Next, I will comment out the swap entry. After saving the file, I will disable swap immediately by running swap off command. Now, if we check the memory, we'll see that swap has been disabled. With that out of the way, installing K3s is a breeze. I will simply run the installation script as root, and that's it, we are done. K3s packages the core Kubernetes components into a single lightweight binary. It includes everything you need, such as the API server, kubelet, scheduler, controller manager, kubeproxy, and more. This binary is roughly 60 megabytes in size. It also bundles Flannel in VXLAN mode as the Container Network Interface CNI and uses SQLite as the storage backend. However, you can easily replace Flannel with other CNIs like Calico or Cilium and swap SQLite with etcd if needed. By consolidating these components into a single binary, K3s minimizes resource usage and simplifies installation and management, making it an ideal choice for resource-constrained systems. Apart from the K3s binary, the installation also provides utilities like kubectl, CRI-CTL, and CTR, which are sym-linked to the main K3s binary. Additionally, an uninstall script is included, making it easy to remove the cluster. The installation process also configures K3s as systemd service that starts automatically after reboot. The kubeconfig file for managing the cluster can be found in etc rancher K3s location. This file contains the API server endpoint, client certificates, client key, and the cluster certificate authority, allowing you to connect and manage the K3s cluster using kubectl or K9s. In addition to the core processes, some components run as pods. There's a DNS server that allows pods and services to communicate with each other using Kubernetes DNS names. We also have dynamic storage provisioner that allows K3s to dynamically create persistent volumes by using local disk storage on the node. Next, there's metric server that collects and exposes resource usage data of the node and pods to the Kubernetes API. Finally, there's the embedded load balancer and Traefik Ingress Controller that manage incoming traffic. Initially, I plan to cover all of those components in detail. However, I've decided to save the discussion for another video. There will be also a separate video on replacing the embedded load balancer with MetalLB using alternative CNIs like Calico or switching to a different ingress controller. So please stay tuned for those. For this demonstration, however, the default installation works perfectly. To summarize, with K3s, you get a production-ready, lightweight Kubernetes distribution optimized for simplicity and low resource usage. Before we proceed with the sample deployment, I'd like to highlight a few important points. By default, the 10.42/16 subnet is used for pods and 10.43/16 subnet is used for services. However, you can override this by specifying the cluster CIDR and service CIDR parameters when running the installation script. Another key detail. By default, K3s uses the Traefik Ingress Controller. It is an oversimplification, but an ingress controller is basically an HTTP reverse proxy that allows clients to connect to your HTTP workloads. In the default installation, a Traefik service of type load balancer is created that exposes the ingress controller on node primary IP on port 80 and 443 TCP. Thanks to that, our clients will be able to access our applications. Let's see how the cluster behaves by deploying a simple application. I have a sample manifest for the WhoAmI application, which returns basic information such as the client IP, request headers, and server hostname. Let's open the manifest file. The deployment definition specifies a single pod running the WhoAmI image. Along with the deployment, we'll create a cluster IP service. This type of service provides a stable internal IP for the pod, acting as a mini load balancer. However, note that a cluster IP service is only accessible within the cluster. Finally, we define an ingress resource. If someone connects to our ingress controller using the hostname whoami.linuxcloudhacks.ovh, traffic will be routed to the WhoAmI service, which then forwards the traffic to the pod hosting our application. Let's apply the manifest. Now let's check the deployment. A new deployment has been created. Next, let's list the pods. You can see there's a single pod running our application. If we check the services, we can see a single service of type cluster IP. As I mentioned earlier, cluster IP services are only accessible from within the cluster. To demonstrate this, let's try to access the service from another machine. As expected, it doesn't work. Fortunately, we can access our application via the Ingress Controller. Let's inspect the Ingress configuration. Here we see that if someone connects to the node IP, that's 192.168.10.230, using the hostname whoami.linuxcloudhacks.ovh and the path / the traffic will be routed to the whoami service on port 80. To clarify the difference between an ingress and ingress controller, the ingress controller is the HTTP reverse proxy that handles the incoming traffic. The ingress resource defines the routing rule for the traffic once it reaches the ingress controller. Let's test this by accessing the application via the ingress controller. First, I will try to call it using the node IP. 404 response. That's because the ingress controller uses the HTTP host header to determine where to route the traffic. Now, let's include the hostname in the request header. And there it is. We've successfully received a response from the whoami application. Let's take a high-level look on how everything is wired. We have a K3s node with the IP address 192.168.10.230 and a client machine with IP address 192.168.80.14. These two machines have network reachability. On the K3s node, there's a pod network with the range 10.42/16. There's also a service network with range 10.43/16. Within the pod network, we have a whoami pod serving our application with the IP address 10.42.0.7. In front of this pod, there is a cluster IP service with the IP 10.43.114.120, which directs traffic to the pod. Behind the scenes, this is implemented as an IP tables rule that forwards traffic to all pods with the label whoami. While we only have a single pod here, in a real-world setup, there could be multiple pods. Note that if a pod is recreated, its IP address will likely change, but the service IP will remain static. Additionally, there's a pod running Traefik Ingress Controller, which acts as a reverse proxy. Naturally, there's also a cluster IP service pointing to this pod. Lastly, there's a service load balancer pod. Its role is to create an IP tables rule that forwards traffic from K3s node's IP, that's 10.230, to the traffic cluster IP service. Now, let's take a closer look at how the data flows. The client makes an HTTP request to K3s node on port 80 TCP. An IP tables rule created by service load balancer pod forwards the data to traffic cluster IP service. The traffic cluster IP service forwards the request to traffic pod running the ingress controller, again via an IP tables rule. The ingress controller inspects the host and path fields in the HTTP header to determine the corresponding rule. Based on the rule, it forwards the request to the cluster IP service of our application. The application cluster IP service then forwards the traffic to the application pod. In summary, it's essentially a series of IP tables rules orchestrating the flow of traffic. Let's expose our application outside the cluster. Naturally, we want to use domain names instead of IP addresses. Fortunately, when using a domain name, the hostname field in the HTTP header is populated automatically. To test this, I will try accessing our application from my home PC. As expected, we get an error. The domain could not be resolved. This happens because we haven't assigned any IP address to this hostname yet. Let's confirm. No IP is associated with this hostname. What if we assign the IP of our ingress controller to the domain? Let's do that. I'll go to Cloudflare console and create an A record for whoami pointing to 192.168.10.230. That's the IP of our K3s host. Now, let's check if the domain resolves correctly. Great, it now points to our K3s server. Let's rerun the request. Success! We got a response. However, there are two issues with this setup. Currently, we can't see the real source IP of the client. Instead, the X-forwarded for header shows the IP of the CNI0 interface. This is easy to fix by updating the traffic service configuration. Let's edit the traffic service and change the external traffic policy to local. I have a dedicated video on this topic if you are interested in the details. Now, let's repeat the test. The X-forwarded for and X-real IP headers correctly show the client source IP. The bigger problem is that this setup only works within our local network because the ingress controller IP, that's 192.168.10.230, is private and not routable over the internet. To make it accessible globally, we need to configure port forwarding on the router. Let me open the router's console and go to the NAT configuration. I will create a new port forwarding rule named Traefik. Set it as a destination NAT rule. Forward TCP traffic on port 80, arriving at WAN1 interface to the K3s nodes IP 192.168.10.230 to port 80. Let me click apply. I will also clone this rule and forward traffic on port 443, that's HTTPS. With the changes applied, the next step is to update our DNS record to point to the public IP address of my router instead of the private IP. I will go to DNS console and replace the private IP with the public one. Let's verify the DNS update. Now, the domain resolves to my public IP. Let's test it again. It works. Traefik also accepts SSL on port 443, so let's try accessing the application using HTTPS. It fails because we are using a self-signed certificate. To bypass this, we can skip certificate validation by using the -K option. There you go. Our service is now exposed to the internet over both HTTP and HTTPS using a self-signed certificate. And the X-forwarded4 header shows the true source IP of the client. A quick note, if your client and your K3s server are on the same local network, you'll need to set up a higher pin NAT for the configuration to work. If you are interested in how to set it up, please let me know in the comment section. My configuration does not need hairpin NAT, as K3s and the client are on separate networks. Okay, you will say, there's no real SSL certificate, there's no HTTP to HTTPS redirection, moreover, not everyone has a public IP available. That's true. However, if you have a public IP, then Traefik Ingress Controller can issue and manage Let's Encrypt certificates natively. It can automatically issue, renew, and store certificates for your services. I will show you how to set it up in one of my future videos. This is not what we'll be doing today. We'll delegate exposing the services to the internet, SSL certificate, as well as HTTP to HTTPS redirection to Cloudflare. To do that, we'll set up an encrypted tunnel between our K3s node and Cloudflare infrastructure. Cloudflare will accept TLS connections from our clients and then proxy the traffic through the tunnel back to our Ingress controller. With this approach, we don't need a public IP or a certificate, all will be handled for us. Let's get to work. First, I will go to the DNS console and remove the A record for WhoAmi application. Then I will go to my home router and remove both rules that did port forwarding. Next, let's install CloudflareD. That's a lightweight daemon that establishes a secure outgoing tunnel to Cloudflare global network. To do that, I will first add the package signing key, then I will add Cloudflare repo to apt repositories, and finally install CloudflareD. Next step is creating a tunnel. First, we need to authenticate our CloudflareD instance with our Cloudflare account so we can create and manage the tunnels from this machine. To do that, let me run tunnel login command. Then I will open the URL, select our domain, and click Authorized. Next, let's create a tunnel from the server to Cloudflare. I will issue tunnel create command and name the tunnel my tunnel. This command created a tunnel and saved the credentials in CloudflareD hidden folder. Now, I will create a secret in Kubernetes named tunnel credentials and store credentials from this file in that secret. Finally, let's deploy CloudflareD into the cluster. I have a manifest file ready. Here we find just a simple deployment with CloudflareD image. Only interesting thing is that we mount the configuration file as a config map. Let's look at that config map. We use myTunnel, we read the credentials from the secret created earlier, then we define a rule that any host name that ends with Linux Cloud Hacks OVH should be directed to our Ingress controller. Mind that this configuration is for the reverse proxy on Cloudflare side. Let's apply the manifest file. If we look at the Cloudflare console, we see the tunnel being healthy. Let me try calling the service. It does not work. To be expected, we don't have a DNS entry for that domain. Instead, let me point that domain to the tunnel. To do that, we just execute CloudflareD tunnel route DNS command, followed by the tunnel name and the domain name. That will create a CNAME that points to any domain that ends with Linux Cloud Hacks OVH to the tunnel. Now let's check the IP for that domain. Points to Cloudflare. To be specific, due to the CNAME that we've defined, any domain that ends with Linux Cloud Hacks will point to our Cloudflare tunnel back to our Ingress controller. So basically, any application that we expose with Ingress will be automatically available to the internet. Once this is done, let me call our application. HTTP does not work. We need to use HTTPS. That's because we've selected Always Use HTTPS in the SSL TLS Edge Certificate section. Let me rerun the request, this time using HTTPS. Works. If we scroll up, we'll see that the certificate is okay. Of course, instead of using wildcard CNAME, you can add individual records, one per application, as it's just a single command. I've added a wildcard CNAME just for convenience. And that's it. Now you can deploy any application to your Kubernetes cluster and expose it to the internet, with Cloudflare handling TLS offload for you. To demonstrate, let's look at a quick example. I should have started with. I have an Uptime Kuma deployment manifest ready to go. Here's the Ingress definition. The subdomain uptime.linuxcloudhacks.ovh points to the uptime service. Let's apply the manifest and wait a few moments for the pod to start. Once it's up, I will navigate to the domain name we defined in the Ingress, and it just works. Deploying and exposing applications takes no more than a few seconds. How cool is that? Of course, don't forget to configure Cloudflare's web application firewall to secure your application and use Zero Trust to enforce authentication. We'll cover these topics in future videos, along with Metal LB for load balancing. If you found this video helpful, don't forget to like, subscribe, and hit the notification bell so you don't miss upcoming content. I'll be diving deeper into Kubernetes, Cloudflare, and more powerful tools to make your deployments faster, easier, and more secure. Thanks for watching, and see you in the next one.